Audio Jungle. Audio Jungle.
Fine. So, last lecture we had seen Mohr circle, and today we have to discuss about the plane stress condition, plane strain condition. We have to discuss the equilibrium equations for the 2D system, and then we'll talk about the compatibility equation and airy stress function. These are the topic we are going to discuss today. So, if you say discuss about the plane stress condition or plane strain condition, so it's very simple. See, plane stress or plane strain condition, generally if I say plane stress, okay, that means is what biaxial stress system or 2D stress system. So if you are saying plane stress condition, so it means you are going to write the condition for the 2D stress system. Okay. Similarly, if you talk about the plane strain condition, so plane, that plane meaning itself is what you have converted that object 3D object into 2D. That's the reason it is plane. Plane means XY plane, YZ plane, or ZX plane. But if it is 3D system, then you cannot say it is plane. It will not be a plane that time, because plane means it may be XY plane, it may be YZ plane, but or it may be ZX plane. But if it is XYZ, all three dimension if you have, then it cannot considered the whole system as a plane. So if it is 3D, then to consider as a plane for that system, you need to consider 2D. Any one axis you can make equal to 0, or you can say you are neglecting that, or thickness is what negligible, any one axis. I'll tell you. So suppose we are talking here plane stress. Okay, so now XYZ axis we have. Now for this XYZ axis, this is the block. Okay, so generally if you check this plane, so here we have this one. I'm considering this plane. This is what Y, this axis is what Y axis, and this axis is what X axis. So this will be called as a XY plane. Hope you understood. Only this I can say this is A, B, C and D. So that XY plane is nothing but A, B, C, D plane. Okay. Similarly, anyone, I can take this one. If you say this plane, we can take, see here. Okay. So this one, this is called, this length is what X, and this length is what Z. So this is called X Z plane, which is nothing but A, B, F, E. A, B, F, E plane is nothing but XZ plane. All right. Similarly, we can have the next, which is third one. It is nothing but this plane. This is what, see, this axis is nothing but y, this axis is nothing but z. Okay, so this is what, yz plane, and this is what AD, just say PQ, PE. Okay, so this YZ plane also called as ADPE. So this plane is nothing but YZ plane. If you check for all, if it is YZ plane, so for YZ plane what we have on YZ plane, that x is what, 0. Similarly on XZ plane, XZ plane, what is the y? Equal to 0. XY plane, then on XY plane, what is the z? Equal to 0. So generally if you say plane, okay, if it is 3D system and you are going to talk plane, that means you are considering only 2D system. You have 3D system, but if you want to convert that 3D into 2D, then you have to mention the condition which is called plane stress. See, for all the planes we will have a stress system. Okay, generally for the 3D stress tensor I had explained, for all the phases I had explained the stresses, tau, sigma xx, tau xz, tau yz, all, everything I had explained. Okay, so based on that, if you are saying plane stress, so that plane stress means you are talking about the 2D stress system, and we are very habituated with the xy plane. That's the reason if you talk about the plane stress, then z axis you will consider as a 0. So now this 3D system will be converted into the plane, and if you are talking about the xy plane, so this will be the xy plane here. Check, this is the xy plane, x and y. If you check here, z will be 0. So what is the mean? Mean is what? Thickness is negligible, or you can say 0, or perpendicular to, if I say xy plane, it means thickness perpendicular to xy plane 0. That's the mean of the xy plane, right? So in the same way I had explained the stress system for the 3D. If you want to show the stress system for this xy plane, so this will be what, sigma xx in this direction, which is the y direction. So in this direction it will be tau xy, and this will be tau x z. Already I had shown you for the, in my previous lecture I had shown that stress system, okay, for all the phases if it is 3D. Now so if you talk about the plane stress condition, so plane stress condition means perpendicular to xy plane, means in z direction all the stresses will be 0. So if you write 3D stress system, so if you check 3D stress system we have here.
Sir, previous slide one. Yes, sir, done.
So 3D stress system, if you check here, so it is nothing but sigma xx, tau xy, tau xz, tau ix, sigma yy, tau iz, tau zx, tau zy, and sigma z. This is the 3D stress system, or you can say stress tension for the 3D system, right? Now if you want to convert it into plane stress system, plane stress, you are going to write plane stress means what? Means all the stresses in z direction will be 0 for the plane stresses. So you are considering xy plane, for xy plane, okay, for xy plane, because you are very habituated for the xy plane. So I am considering here xy plane. It doesn't mean plane stress means only xy plane, any plane, xz plane or yz plane. If you are considering yz plane, then in x direction stresses will be 0, like sigma xx will be 0, tau xy will be 0, tau yx will be 0, tau xz will be 0, tau zx will be 0. Where x term will come, that stress will be 0. That's the mean of it. If I say xz plane, and for xz plane you are writing the plane stress condition, so all the stresses in y direction will be 0, like sigma yy will be 0, tau yx will be 0, tau yz will be 0, tau zy will be 0, tau xy will be 0. Okay, so but you are very habituated for the xy plane, so I am considering xy plane. Hence in z direction all the stresses will be 0, so I am considering sigma zz 0, tau xz 0, tau yz 0. Obviously if you check complementary stress, so tau xz means tau zx will also be 0. Tau yz, so complementary stress tau zy, this will be 0. So if you convert this into plane stress, so you will have the stress system like this: sigma xx, tau xy, tau yx, and this is what plane stress on xy plane. Hope this one is clear. So this condition itself called as plane stress. So conversion, you can say, from 3D to 2D, that will be considered as a plane stress condition. And why you are considering this plane stress condition? As I told you, 3D stress system calculation point of view, it's very complicated. So what you will do, you will consider as a plane stress condition, means you are assuming that it is only 2D system. So any third axis you can consider as a 0. So for a plane stress problem, component of stresses are perpendicular to the plane of plane stress problem are 0. But doesn't mean that strain will also be 0. No, that strain will not be 0. That strain will not be 0. Okay. If you check, this is the first thing, this is the condition for the plane stress condition. Similarly, we can write the equilibrium equation for the plane stress condition. So what is the equilibrium condition? So we have equilibrium equation, we have to derive, but I will not derive directly. I will write the equilibrium equation. Okay, so you will understand easily. So plane stress condition you will apply for the equilibrium condition also. So first I will write equilibrium equation here. Equilibrium equation. Okay, so if you are going to write the equilibrium equation, so we will consider one stress system here. We can take xy axis here. This is x-axis, this is y-axis. One time they had asked about the equilibrium equation, so we should know. Okay, we should know that equilibrium equation in examination they had asked to us. What is the equilibrium equation and all. So as I mentioned you, that derivation, it is not required. The thing is, for the 3D stress system you can convert into 2D stress system. So one plane you will get, and plane will be like this only. For xy plane, From where you will get this? You will get from the 3D system and you convert it into 2D. So this plane you will get, okay, XY plane. Now for this, if you check the stress system, so definitely this will be the, you can say, sigma xx, and obviously this distance is nothing but delta x because it's x axis, and similarly we have delta y, and this is the center point of this, okay. We will have sigma xx plus, because of the length, dou by dou x, sigma xx into delta x. If you make delta x equal to 0, then again you will reach at this face, which is nothing but a, b, c, d. So you have written this equation in the terms of the length, because if you make delta x is equal to 0, you will be on AD phase. Make delta x is equal to 0, so you will have sigma xx, means what is the stress on the AD phase, same stress you will get with this equation also. But if you write delta x some distance, you just say AB length, then again you will reach to the BC phase. So this is the way to write the stress system with respect to the length, okay. Similarly, we will have here this, because it's a y-axis, so this just say this is the sigma yy, and obviously here it will be sigma yy plus dou by dou y sigma yy into this vertical length is nothing but delta y, so make this delta y. So this is the way to write the stress system, and this is the origin, okay. This is the origin or center, you can say. All right. Now if you want to write the stress system for this, so you have to assume the body force, okay. And the body force here you can write in the, you consider that body force we have here, it is xyz, okay. And this body force is what? Basically per unit volume, okay. So we can consider body force per unit volume are x, y, okay, and z if it is 3D, but we have considered as a 2D system here. This is the 2D system, okay. This is the 2D system, but I will write the equation for the 3D system. You can convert, make z equal to 0. So I'm just writing the general equation here. So consider body force per unit volume are x, y, and z in x, y, and z direction respectively, okay, respectively. Now what you will do, it's a simple only. If you write the equation, which is the equilibrium equation, in any direction you can write the all the force balancing. You can take x direction, similarly you can take y direction, and in z direction. So for x direction, if you write that equilibrium equation, so it will be equilibrium equation in x direction, and the equilibrium equation will be, this is the derivation, this step I am writing directly, okay, not required derivation, dou sigma xx divided by dou x plus dou tau xy divided by dou y plus dou tau xz divided by dou z plus in x direction body force is x, then equal to 0. This is the first equilibrium equation, and I'm writing this equation for 3D, okay? And this diagram is what 2D basically. I have converted that 3D diagram into 2D. If you go for the 3D, then this diagram you may get. This diagram you may get. All faces you will have a 3 stresses: sigma xx, tau xx, tau xy, and tau xz. Similarly, on upper face also you will get 3 stresses. Okay, so that already we had discussed in previous lectures. You can watch that video, then we will get that. Anyway, what is the equilibrium equation in y direction? So in y direction, that equilibrium equation will be dou sigma y divided by dou y plus dou tau yx divided by dou x plus dou tau yz divided by dou z, and this is in z direction, so body force will be z. This is in y direction, so in y direction the body force will be y equal to 0. This is the second equilibrium equation. All right, similarly we'll go for the z direction. So the equilibrium equation will be dou sigma zz divided by dou z dou tau zx divided by dou x plus dou tau xy divided by dou y, and this is in z direction, so body force in z direction will be z is equal to 0. So this is the equation number 3. Reference book here from where I am taking these notes, it is TSG Maxon aircraft structure. So full derivation they have given step by step. It's not complicated, it's very simple only. Only you need to take the force balancing in XYZ direction. If you do, then XYZ direction you will get the stress. All right.
Yes, sir.
Yes, this is the actually for the time saving purpose I have written these steps directly. Otherwise you can derive it also. So this is
Sir,
yes.
for 2D, what?
Yes, I will write the equation of equilibrium must be satisfied at all interior points in a deformable body under 3D force system. Okay, so whatever the equilibrium equation you have written, it is for the deformable body. Okay, it is for the deformable body. Always remember, this is for 3D system. For 2D, or you can write, this is the notes you need to remember. Okay, you can write, this is the notes, very important, exam point of view. You can write here equilibrium equation for plane stress condition. What is the plane stress? It is 2D. So they can ask you how many equilibrium equation for the 2D system they can ask, or they can say like how many equilibrium equations for the plane stress condition. If I say plane stress condition means it's a 2D stress system, and I already had explained for the plane stress condition how many stresses are zero. 3 stresses. What are they? They are sigma zz 0, they are tau xz 0, and they are tau z. If I say tau xz is 0, then obviously tau zx will also be 0 because it's a complementary stress. If it is tau yz is 0, then obviously tau zy will also be 0 because of the complementary stress. Apply these for the equilibrium equation. So check. We have dou sigma zz will be 0, dou tau zx will be 0, and this is what zy, not xy. This is zy. Is correct? This, I think I made mistake. This is the zy. So tau zy will also be 0, and obviously body force in z direction will also be 0. Okay, just correct this. See, like sigma y by tau yx tau yz. So this is sigma zz tau zx tau zy, no? And in previous also it's sigma xx tau xy tau xz. Okay, so tau xz will be 0 here. Here tau yz will be 0. Here sigma zz will be 0, tau zx will be 0, and tau zy will be 0. So how many equilibrium equation you will get? Yes, tell me, dear.
Sir, capital X, Y, Z, these body forces will remain same, no?
No, if you are considering only 2D system, then that body force z direction will be 0 also. You are not considering that. You do not.
Sir, let's suppose for Y direction, if you write 2D for, so this capital Y will be 0.
No, capital Y will not be 0. Like you are considering XY plane, so X force and Y force will be there, but Z force will be 0.
Yes.
Understood? Yes.
Yes, sir.
So now how many equilibrium equation you have? 2. You need to write. This is very important. Okay, this is very important. So that equilibrium equation I need to write here. These are the dou sigma xx divided by dou x plus dou tau xy divided by dou y plus force x is equal to 0. And what will be the second now? Second will be, check this part. You check here, only tau yz will be 0, rest part will be there. So it will be dou sigma yy divided by dou y plus dou tau yx divided by that's all. These 2 equilibrium equation you will have, okay, when it is plane stress condition. Always remember, when it is plane stress condition, then these 2 stresses will be there. Hope this one is clear. We'll need to find how many strains are available for the plane stress condition. So first of all, we should know the number of strain. So generally strain, here it is divided in 2 parts called longitudinal strain and shear strain. Shear strain always acting on plane. Okay, it is acting on the along axis. If it is 3D systems, for the 3D stress system, so how many axes will be there? X, Y, Z. So along axis, one will be along axis, along X axis, one will be along Y axis, another will be along Z axis. I'm considering X axis in short I am writing here. So along x axis the strain will be epsilon x and it will be dou. Along x axis what are the displacement? Let me write this also. This is x axis, check, this is y axis and this is z axis. So along x axis the displacement will be u, along y axis the displacement will be v, along z axis displacement will be w. Okay, so what will be the longitudinal strain in x direction? So I can say it is along x axis the changes displacement is suppose delta u. Okay, and in what distance it is suppose delta x distance, the change in displacement is what? U. So you can say that longitudinal strain, you might have seen this formulation in fluid mechanics, so that longitudinal strain will be dou u by dou x. It is in x direction. Similarly in y direction, what is the strain in y direction? It is displacement in y direction is v, dou v by dou y. Similarly in z direction it is longitudinal strain, hence epsilon z is nothing but displacement in z direction is w, dou w divided by dou z. These are the longitudinal strain. Okay, or sometimes called linear strain, sometimes called normal strain, linear strain, longitudinal strain. All right, but what about the plane? So definitely we will have a plane, maybe xy plane, yz plane or zx plane, just like I had shown you here in the diagram. See, maybe xy plane here, maybe xz plane or maybe yz plane. These are the planes, xy plane, xz plane or yz plane, right? So I can mention here for the shear, we can say this is what first I will write for the xy plane. Okay, for the xy plane. So now because it's a shear stress, so shear stress, you know, longitudinal strain was denoted by epsilon and shear strain will be denoted by gamma. Okay, so because you are going to talk about the xy plane, that shear stress will be gamma xy. Okay, it's gamma xy, or you can say gamma like this, gamma xy. What will be the shear strain? So gamma xy will be, it will be because x we have, so it is x plus this is y, so this is y. In this way you need to remember, make this cycle x, y and z. Okay, for x what is the displacement? It is u. For y what is the displacement? It is v. For z what is the displacement? It is w. So in case of shear strain, this is the dou x, and because it is gamma xy, so x we have, so dou x in denominator, y we have, so dou y in denominator. Just opposite, what is the displacement in y? It is v, so dou v. What is displacement in x? It is u, so dou u. So I'm telling you the trick how to remember, but this is the derivation. Actually derivation not required. In fluid mechanics also we had derived shear deformation and all. So in the same way this is also we can derive here. It's not required actually. Similarly we can write xz plane. So xz plane means what? Gamma xz. As I told you, it is x, dou x, dou z. Dou z in z direction, what is the displacement? It is w, so dou w. In x direction, what is the displacement? It is u, so dou u. Okay, this is the gamma xz. Now next we have yz. So in yz plane it is gamma yz. Check, we have dou y, In z direction, what is the displacement? It is w. In y direction, what is the displacement? It is v. So how many strain you got? Total 6. Number you need to remember, 6 strain you may have. Okay, total number of strain we have 6. 3 longitudinal strain we have and 3 shear strain we will have. You always remember this formula. Okay, these are the strains. These are the strain you need to remember. All right, and I had given the and this type of relation, it is, this relation is what, between what? So displacement you have basically u, v and w, yes or no? Now I will like explain here once again for gate point of view, like what in gate they had asked. So first of all you need to remember, this is the axis, 3 axis, x, y and z. In x direction displacement is what u, in y direction displacement is what y, v. So now the relation you are going to write, this relation called as strain displacement relation. What it is called? Strain displacement relation. Okay, now you already have written this relation previously. So first you write longitudinal strain, so epsilon x is nothing but dou u by dou x. Check, epsilon is the strain, u is the displacement, it becomes a strain displacement relation. All right, second, epsilon y, dou v by dou y. Third, it is dou w divided by dou z. This is the one, strain displacement relation. Coming to fourth, xy plane, hence gamma xy, dou x plus dou y, this is v, this is u. After gamma xy you will have a gamma xz, dou x plus dou z, this will be dou w, this will be u. Next is gamma yz, so this one you need to remember, this is very important. Okay, this is very important what I have given to you here. Make it in box. Strain displacement relation. How many we have? 6. Okay, where u, v and w are displacements in x, y and respectively. All right, first you need to remember, this is very important. All right, now in my previous lecture also I had discussed about the relationship between stress and strain. So this relation is called as a strain displacement relation. How many strain and displacement relation we have? Total 6. Okay, how many displacement we have? Only 3. U, V, W are the displacement, so 3 displacement we have, and how many strains we have? 6. Please remember, this is very important, they had asked in examination. Okay, now coming to the relationship which is called as strain stress displacement, strain stress relation or stress strain relationship. Sometimes it is also called constitutes relation, some in few books you may get it. Okay, so next we'll write And this all will help for plane stress and plane strain condition and compatibility equation. All these equation will be helping for us. Okay, so write neat and clean and we'll connect it. Anyway, so now we are going for next, which is called stress strain relationship. Okay, or it is also called constitutes a relation. It's a relation between stress and strain. Okay, like if you talk about the stresses, so strain, you have seen how many stresses you have, you know that, which is called normal, or sometimes called direct stress, and third is shear stress, or sometimes called tangential. If we have a 3D system, what are the stresses in x direction? Sigma xx, sigma y, sigma z. Similarly, we have a tau xy, tau xz, and tau yz. Complementary stress, if you write tau zy, tau zx, yx. So here you can consider is three stresses we have here: shear, and three stresses we have a normal. Okay, 3 plus 3. Now if you develop the relationship between the shear stress and shear strain, then what you will do? For that, I had given in my previous lecture, if you check, it was the stress strain relationship. How to write this? So you just remind, you may get, because already I have given this equation. So if you take any this is what bar, okay. Now we have the axis, x, y, and z. So I can say this is what sigma zz, sigma yy, and sigma xx. And obviously because of these stresses, we will have a strain in x, y, z direction. So based on how many stresses we will have, six strains, 3 normal strain and 3 shear strain. So all 3 I will write here. Okay. Normal strain and shear strain in terms of stresses. In terms of stresses, we are going to write number 1. Normal stresses along x direction, it is epsilon x because of all 3 stresses. So I had explained already how you can write this: sigma xs by E minus Poisson ratio. I had explained. Poisson ratio, it will come because of the lateral strain. So mu sigma yy divided by mu minus sigma HZ divided by E. Similarly, you can write epsilon YY, or epsilon XX you can write, or epsilon YY, it's your choice. Sigma YY by E minus mu sigma XX by E minus mu sigma ZZ by E. Third, it is sigma ZZ divided by E minus mu. So this is the normal strains and stress relation. How to write that relation between stress and strain? It's very simple, 3, and this is number 4. Okay, that shear strain and shear stresses gamma xy on xy plane, these are along xyz. Normal strain always along xyz, shear strain always for the plane, and this always along axis, x-axis, y-axis and z-axis. Shear strain always for the plane xy plane. So if you relate with respect to the stress, so it is tau xy shear stress divided by modulus of rigidity G, capital G, if you remember, phi number. Now next plane will be the xz plane, so gamma xz plane. So this shear stress on xz plane tau xz divided by modulus of rigidity capital G. Number 6. Next plane we have here gamma yz. So shear stress on yz plane divided by modulus of rigidity. So how many constitutes relations we have here? Total 6, or we can say stress strain relationship. If you check how many we have, total 6. This number you need to remember here. How many displacement you have? Displacement, 3 displacement. U, B, W. So how many displacement we have? 3. How many stress strain relationship we have? 6. How many stress strain relationship we have? 6. These are the points you need to remember. Okay, it is very helpful, very helpful. All right, write the number. See, the what I have written, tau xy and tau yx are the complementary stress. So actually it is equal and opposite, but if you check the number of stresses for the shear, then total number of stresses we will have 6, 3 plus 3. Okay, don't go for like, okay, tau xy and tau yx, so consider 2 stresses. So if I say total number of stresses, how many stresses we have, so you have to say total number of stresses we have 6. You got my point or not? That's the point. Yes, yes, there should not be any confusion. So just like a strain we have a 6, similarly we have a 6 stresses also. Okay, that complementary stresses don't consider 2, tau xy and tau yx, so hence it is 2. Tau xz and tau zx again 2, 2 plus 2 4. Then again tau yz and tau zy, it is 2 plus 2 6. Don't consider 6 shear stresses. Consider 3 shear stresses and 3 normal stresses. Total we have 6 stresses. So generally, now if you check in this balancing, what we have balancing here, so if you check the number of equations and check number of unknowns, okay, equations and unknowns, so you may get here total number of equations. First we'll talk about the equilibrium equation. equilibrium equation we have 3. Second, we'll go for the strain displacement equation. Just now we have seen it is 6. And third, we have a constitute which is also called stress strain relation. Just now I have shown you it is 6. This is the constitutes relations. Okay, 6. So if you check total number of equation, we have 15 equation. Okay, now coming to this unknowns. How many unknowns we have to check that? Total number of strain, how many strains we have? We have 6 number of strains. For any body, geometrical body, if you are going to calculate, so for the 3D, I am saying for the 3D system. So how many strain you may have for the calculation? So 6 strains you need to calculate for the 3D system. I have shown you number of strains, 6. Similarly, how many displacements you need to calculate for the 3D systems? It is 3. And how many stresses we have here for the 3D system? I have just now I have shown you it's 3 plus 3, 6 stresses we have. Okay, so total number of unknowns we have 15 unknowns. Hope you understood. Like for any 3D systems, because we have 15 unknowns. Unknowns are in front of you. They are asking in examination. Okay, equilibrium, strain displacement, constitutes relation 3, 6, 6. These combination they had asked in examination. So total unknowns we have total 6 plus 6 plus 3. 15 unknowns we have. To solve these 15 equation, 15 unknowns, to get these 15 unknowns for any 3D structural body, we required 3 equations. And these equations are 3 equilibrium equation for the 3D systems, 6 strain displacement relationship, and 6 constitutes relation, which is also called stress strain relations. This is also called stress strain relation. Need to remember. These are the balancing. So these must be solved for a generic body under some generic loading subjects to prescribed boundary conditions. Okay, 2 types of boundary condition we will have: normal and geometric. Normal means maybe stress they have prescribed for the systems, for the objects, and second boundary condition maybe displacements they have prescribed. If they have, that is called geometric boundary condition. Okay, so if geometric boundary condition means displacement they have prescribed, so from the displacement you have to start. With the help of displacement you can get the strain, because we have a strain displacement relation. Once you get the strain, then you have stress strain relationship. With the help of strain you can get the stress. So these are the working process for the unknowns and for the number of equations. So total for any 3D systems, they had asked one time in exam, in 3D system, structural body, 3D systems, total number of unknowns we have 15. To solve these 15 unknowns, we have 15 number of equation, and with the help of these 15 number of equation, we can get the result. And obviously boundary condition will be given to us, and that boundary condition will be given in 2 ways. One, maybe stress they have prescribed, another maybe displacement they have prescribed. If they have prescribed displacement, then it is called geometric boundary condition, and if they have prescribed stress, then it is called as normal boundary condition. Hope this one is clear to all. Done. So now for the plane stress, we had seen for the plane stress condition, If I say for the plane stress condition, so how many equilibrium equation you had seen? There are two equilibrium equation in plane stress condition. In plane stress condition, somewhere here you have written, in plane stress condition we have two equilibrium equation. This is the one thing, two equilibrium equation, okay, pointed. All right, now if I say for the plane stress condition, how many strain displacement equation? How many strain displacement equation? So again, this is the number one case. I think I should say from here the story is what started. So I can say this is the case one. Okay, this is the case one. Now I am going for the case two. After explaining all those things, I am just going for case two. What is case two? For the plane stress condition, how many strain displacement equation we need to get? A strain displacement. Now easily you can identify because everything I have given to you in front of you, and this type of question they are very frequently asking in our examination. Okay, so we'll check strain displacement equation. Where is the strain displacement equation? These are the strain displacement equation. Check if it is the plane stress condition. If I say plane stress condition, right, then what will be the stresses? Plane stress condition, for the plane stresses condition, what will be the stresses? Check here, we are not getting any stress function here, only strain we are getting, check, only strain we are getting for here in this case. So we will go for the condition for the plane stress condition. How many strains are available? How many strains are available? That we need to find. Okay. So for the plane stress condition, we will have a tau x z is equal to 0 and tau yz equal to 0. Once tau xz and tau yz is 0, then what will be the gamma xz and tau gamma yz? This will also be 0. So we know gamma xz is equal to what? Tau xz divided by modulus of rigidity. This will also be 0. Similarly, gamma yz, tau yz divided by g, this will also be 0. So for the plane stress condition, two strains are also 0. That strains are gamma xz and gamma yz. Now check strain displacement relation. Gamma xz and gamma yz are 0. Gamma xz and gamma yz are 0. Sorry, here gamma xz and gamma yz are 0. So how many plane strain displacement relation we have? 1, 2, 3 and 4. So 4 strain displacement relation we will have. Okay, that were these number we were finding. So 4 strain displacement, 4 strain, and in fact epsilon z will be 0. Anyway, we'll find this epsilon z will be 0 or not. Let us find from where we will find. Check. For the plane stress condition, sigma x, sigma y, this will be 0. Here sigma z will be 0, so this part will be there. Sigma z will be 0, but this, so for the plane stress condition, epsilon z will not be 0. Check here, you can get from here. No, from the equation only you can get. So epsilon x will be there, epsilon y will be there, epsilon z will be there, and gamma xy will be there. Gamma xy will be there. Okay, so I should write here gamma xy does not equal to 0, epsilon x does not equal to 0, epsilon y does not equal to 0, and epsilon z does not equal to 0. So how many strains we have? 4. So total 4 strain we will have. and for this we will get the strain displacement relation. So this relation we will get, for the plane stress also, and this relation we will get. So I can say for the for the plane stress condition, total number of strain displacement equation we will have a 4. What are that? They are, let me write here, they are only epsilon x, which is nothing but dou u by dou x, epsilon y, which is nothing but dou v by dou y, but okay, anyway, now if you talk about the strain here, this value, which is nothing but gamma xy, so definitely this part is nothing but dou v by dou x plus dou u by dou y. One thing, remember, because see here you can say this stress strain relationship, this epsilon zz will be there. Why? Because sigma z becomes 0, but sigma xx will be there and sigma y will be there. So here epsilon zz you will get. But in case of the displacement term, this value will not be feasible. Why? It is not feasible. Why? Because z axis you are not considering, so dou w by dou z, so definitely you will not get any displacement in z direction. So epsilon z, in the sense strain displacement, you will have only 3, because see epsilon z is showing dou w by dou z, which means the displacement in z direction. Okay, so strain displacement only we will have a 3, but it doesn't mean this epsilon z becomes 0. Epsilon z we will get because of this lateral stress, okay, in lateral direction, sigma xx and sigma yy, because of this only, this epsilon zz you will get. So I'm saying strain in z direction you will get, but my point, listen, my point is that strain displacement relationship in z direction will not be feasible, because it's a plane stress condition, so z axis will be 0, hence there is no displacement in z direction. Hence how many strain displacement relation you will have? You will have only 3. Let me write here, only 3 strain displacement relationship. This one is clear or not, dear? Tell me.
Sir, 2 na,
See,
x z and y z.
this part will be there, this part will be there, and this part will be there. This is not possible because we are talking plane stress. So I'm saying strain displacement equation is not possible. That third equation is not possible because it's a plane stress condition. I'm considering z in z direction, that thickness is 0, hence there is no displacement in z direction, there is no w actually, hence epsilon z will be 0. So this equation will not be possible, but it doesn't mean will not get any strain in z direction. Will get in strain in z direction. It is because of the lateral strain. Check, this is the lateral strain, see epsilon zz, this mu sigma xx by e, this is lateral strain, mu sigma y by e, this is the lateral strain. Sigma z will be 0, that is okay for plane strain, but because of these two component we will have epsilon zz. Hope you understood this.
Yes, sir. Yes, sir.
So I'm saying that strain displacement third equation will not be possible, but it doesn't mean we will not have any strain in z direction. We will have, but strain displacement we will have only 3: epsilon x, epsilon y, and gamma xy. Hope this one is clear. Now this is the one very important case. So how many strain displacement relationship you got here? Total 3. Listen carefully. Okay. Coming to the next, we will find case 3. So case 3 we have, for the plane stress condition, we will find constitutes equation. How many constitute equation will be there? Constitute equation means stress strain relation. So already I have given all the equations so that easily you can compare. Otherwise, if I will tell number, then sometimes you may forget that. Better if write all equation, you can analyze by your own. So check. These are the stress strain relationship. See here. For the plane stress means all tau xz, tau yz will be 0, sigma zz will be 0, sigma zz here also it will be 0, sigma zz will be 0. Okay, so here epsilon xx is equal to sigma xx by e minus mu sigma yy by e. This part will be there, sigma zz becomes 0. Similarly, epsilon y we will, this two components you will have. Epsilon zz also, first component sigma zz will be 0, but last two components will be there, so epsilon zz will also be there. Okay, coming to the points, which is nothing but this gamma xy is equal to tau xy by g, and gamma xz equal to tau xz, gamma yz is equal to tau yz. So this part here it is 0. So how many stress strain relationship you may have? You may have here, check. For the 3D I'm saying it's a 4, no? Tau gamma xy, tau xy by g will be there for the xy plane. Rest epsilon zz will be there, epsilon yy will be there, and epsilon xx will be there for the plane stress condition. Yes. So for the plane stress condition, we will have this value. Let me write this. These are nothing but epsilon xx or epsilon x, which is nothing but sigma x by e minus mu sigma y by e epsilon yy So total number of stress strain relationship we will have 4. So for the plane stress condition, these things you need to remember. Okay, so this is all about the plane stress condition. Similarly, we will have a plane strain condition also. Similarly, we will have a plane strain condition also. So how to how to identify that condition for the plane strain, how many functions will be 0, stress or strain, how it will be 0, that we need to write directly here. In fact, for the plane strain, before going to plane strain, we will write the compatibility equation, which is very important. So why the compatibility equations are there, that there is also a reason. Okay, there is a, so first we'll see the compatibility equation. Here we will have compatibility equation. First let me finish that, then we'll see the plane strain condition. Compatibility equation. Okay, so these are the basically relationship between the strain and a displacement. Okay, already we had seen the relationship between the strain and displacement. 6 strains are defined in terms of 3 displacement function. Already we had seen UVW were the displacements, and 6 strain was epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, and gamma zx. That we had seen. Okay. So now more number of the relationship between the strain and displacement further we can see. Okay, so this derivation basically we have here. So I will write all the 6 number of compatibility equation for the 3D system directly. Okay, that derivation I must say is what not important at all. It's simple only. If you want, you can prefer that TSG action. It is nicely it is derived. It's a very simple only. Okay, so for any 3D system, suppose x, y, and z. Now for x, y, z, obviously we will have a displacement. Just say displacement in x direction is what, u, and obviously it's a function of, because it's a 3D body system, so function of x, y, z for 3D. I'm writing for 3D. Similarly in y direction, what is the displacement v, which is also the function of x, y, z, and similarly in z direction displacements is w, it is the function of x, y, and z. Very simple. All right. Already you have seen that relationship between the strain and displacement. 6 strain and 3 displacements. Okay, now already we had seen. Now the going ahead and again will develop the relationship between the that shear strain and longitudinal strain. That relationship we are going to develop. Shear strain and this longitudinal strain. So we can write here it's a relationship between the shear strain and linear strain. Okay, so here we can write that gamma xy, it was dou by dou x plus dou by dou y. Here we have a dou v, here we have dou u. I told you this is for the xy plane. Okay. Now again, if you check this gamma xy, if you differentiate it, and if you differentiate this gamma xy with respect to x and y, and this differentiation you do 2 times you differentiate with respect to x and y, then what you will get? You will get dou square gamma xy divided by dou x dou y is equal to, check here, this is nothing but dou square divided by dou x is already there, you differentiate with respect to x also, so it becomes dou x square. Dou y itself is there, you can write dou v by dou y. Check, it's very simple. For one compatibility equation I will derive it. Next similarly we can write. Okay, so this is the first time just deriving. So this one, you know, now we know this. In my previous slides you have seen this on xy plane. This is the shear deformation. We have differentiated 2 times with respect to x and y, then we got this. Dou x is already there, with respect to dou x you differentiate, then it will be dou x square. Dou y still is there, this is dou v, so dou v by dou y separately I have written. Similarly here dou by dou y, so with respect to y if you differentiate, then this will be dou square divided by dou y square. Again dou x is left, So dou u by dou x I can write. Check what we will get. So this is what dou square gamma xy divided by dou x dou y is equal to dou square by dou x square, as it is dou square by dou x square. What is dou v by dou y? It's epsilon y. This is the first compatibility equation. Dou square by dou y square. This is dou u by dou x. What is dou u by dou x? It is epsilon x. You already have seen, no? Dou u by dou x is nothing but epsilon x. Everything it is already written. Yeah? Here already I have written everything. So nothing to confuse. See, dou u by dou x epsilon x, dou v by dou y epsilon. So all the equation I have written, you just go back and check. So directly I am writing here. So this is the first compatibility equation I am deriving. 2-3 steps are there. So I am deriving this. Rest you can do by your own. It's very simple. So dou square by dou y square, dou u by dou x is what? Epsilon x. Hence it is dou square epsilon x divided by dou y square. Done. This is the first compatibility equation. So check, this is the relationship between the strain, shear strain and longitudinal strain. Epsilon y longitudinal strain along y-axis, epsilon x longitudinal or linear strain along x direction, and gamma xy is the shear strain on xy plane. So this is for basically xy plane. This relationship you have written for the xy plane. Okay. Similarly, you can write other compatibility equations. So I'm not going to write all. I mean, not going to derive all. Directly I will write this result. Please take it. So in a similar manner, now all equation I'm going to write in short. You need to remember. So my point is, you need to remember how many compatibility equation we have. Okay. So these are the dou square gamma yz dou y dou z is equal to dou square epsilon y divided by dou z square dou square epsilon z divided by dou y square. This is the equation 2. Third, dou square gamma xz divided by dou x dou z is equal to dou square epsilon z divided by dou x square dou square epsilon x divided by dou z square, equation 3. This is also compatibility equation. Then again there is a manipulation, add, subtract, do. So if you do that, then another 3 equation you may get like this: 2 times dou square epsilon x divided by dou y dou z is equal to dou by dou x in bracket minus divided by dou x plus dou times dou of gamma xz divided by dou y plus dou of gamma x y divided by dou z. This is equation number 4. 2 times epsilon y dou times of dou y minus dou times gamma xz gamma xz divided by dou y plus dou times gamma yz divided by dou x plus dou times gamma x y dou z. Equation number 5, 2 times of dou square epsilon x y, hence it is z. This is dou x dou z, because y we have, so this is z, so this is what dou x dou y. You can remember in this way, dou by dou z. Okay, minus gamma xy divided by dou z plus, you can rearrange, it's your choice in what way you want to remember, you can rearrange. So these are the compatibility equation, and as the word you can understand compatible, so basically these 6 equations are compatible, hence it is called strain compatibility equation, and it is compatible to satisfy the solution of any 3D systems for any deformable body. Okay, so total how many compatibility equation you have here? Total we have 6. Now this is the 3D, okay, don't consider 30, this is 6. Total compatibility equation we have 6, okay. And these compatibility equation, as I mentioned, called strain compatibility equation, and these are compatible to satisfy the solution of any 3D body for any 3D deformable body, better to say. So these are the compatibility equation. Okay, now my intention to write what the question they are asking, they are not asking to write compatibility equation or to derive the no, they are not asking like that. They will ask for the plane strain condition, how many compatibility equations are there. So these compatibility equation you have written, it is for the 3D system, it is for the 3D system. Okay, okay, this is for the 3D system. Now if it is plane strain condition, then what will happen? That's the point. For that reason we have written all compatibility equation. So we'll consider plane strain condition, which is just like a plane stress. We are talking now here plane strain, plane strain condition. Okay, plane strain, just like a plane stress we have already seen plane stress. Now we'll talk about the plane strain condition. Okay, plane strain. Anyway, plane strain. So in plane strain, what is the plane strain? So basically for a plane strain problem, the strain component perpendicular to the plane of plane strain condition are 0. That's the concept which is repeating just like a plane stress. Similarly for the plane stress, what we had done, perpendicular to any plane, that any plane perpendicular to any plane, the stress will be neglected or considered as a 0. Similarly for the plane strain, perpendicular to the plane, strain will be neglected or considered as a 0 value. The same thing there, perpendicular to the plane, stress were 0, sigma zz, tau yz, tau xz. For the plane strain, we are considering the perpendicular to the plane strain components will be 0. If it is xy plane, then all the z strain component will be 0. Hope it is clear to all. Now, so plane strain, let me write this. Consider all strain component, all strain components perpendicular to the plane. Oh, not this. What I have written. Let me correct this here. This is PLANE. Okay. But about previous, rest it fine. Okay. Perpendicular to the plane. Consider all strain component perpendicular to the plane will be assumed to be zero. Assumed to be zero or considered to be zero. Okay, like we are very habitual for the xy plane. Now xy plane, this is what xy plane, so that means z will be zero, so means all the strain like epsilon z will be zero. Okay, gamma xz will be zero, gamma yz will be zero, right? Now check all the relations we have to check. Like we'll start from the that what it is called, strain displacement relation. Yes, now we'll check case 1.
Sir, once previous slide. Yes, sir, done.
All right. So case 1, we need to write strain for plane strain. Now check immediately and find how many plane strain condition you may have. So check where is the plane strain condition. This is the plane strain displacement. This is the strain displacement. So strain displacement, so epsilon x will be there, epsilon y will be there, epsilon z will be 0, gamma x will be 0, gamma yz will be gamma xy. Epsilon x, epsilon y and gamma xy will be there. Epsilon x, epsilon y and gamma xy will be there. Okay, we will have only 3. How many relationship you will have for the plane strain? Only 3. That you need to remember this. Remember, and what are they? They are epsilon x dou u by dou x, epsilon y dou v by dou y, and gamma xy. That's all. What are 0? Gamma x z 0, always remember. This is the strain displacement. Only 3 you will have. 1, 2 and 3. Now case 2 will go. Only 3 strain displacement relation you will get for the plane strain. Now we have case.
Sir, previous slide, sir. Yes, sir, done.
We'll go for the case 2. Constitute for plane strain. Check. For the plane strain condition, what are the constitutes equation? Constitute means that stress strain relation. So we have stress strain relation here. This is the stress strain relation. Constitutes. Check. So obviously epsilon z will be 0, but still we'll get this sigma z equation. Gamma xz is 0, gamma yz 0, so this part will be 0. Gamma xy, this will be there. 1 2 3 4. 4 equation will be there. No? 4 equation will be there. I will write all 4. Only 4 plane strain, after plane strain condition, only 4 stress condition will be there. Okay, and what they are, I will write epsilon x. What is the epsilon s? It is sigma xx by e minus mu, sigma y by y e minus mu, epsilon y will be there. It is nothing but sigma y by e minus mu, sigma xx by e minus mu, sigma zz by e. Right? What about epsilon z? It will be 0. So if you check epsilon z will be 0, then what will be the equation? Epsilon z is 0, then what will be the equation? So that if you want, you can write, it's your choice. But in fact, if you make epsilon z 0, then okay, I will show you. Epsilon z will be sigma zz by e minus mu so this part is 0, so you will have this value. So 1 2 this is not 3, this is 3. This is the equation 3. So this equation will be there. This will be third equation. And what will be the fourth equation? It will be gamma xy. Okay, tau xy is g. So total 4 equation you will have. Total 4 equation you will have. Okay. Now what about the compatibility equation? So how many stress strain relations you will have for the plane strain condition? You will have 4, and all 4 I have written here. Okay. Now the question is, how many compatibility equation you will have for the plane strain condition? For the plane strain condition, how many compatibility equation you will have? Check. So here we have a compatibility equation. Now check all. This is the first one. So for the plane strain condition, this compatibility epsilon x, epsilon y, and gamma xy. We do not have any x z component, so this will be there 100%. Definitely this will be there. What about this? Gamma yz will be there 0. Epsilon z will be there 0. Z axis will not be there, so this part also be 0. Gamma xz will be 0, epsilon z will be 0. Here also dou z we have, this part also be 0, you can say. Similarly, gamma yz, gamma xz we have z. So everywhere z terms we are getting. Only one equation we have in which we are not getting any jet components. So I can say for the plane strain condition, only one compatibility equation we will have, for the plane strain condition, So case, I think it should be 2, 3. Case 3. Compatibility equation for plane strain. So I can say only one compatibility equation you will get for the plane. This is very, very important. They can ask to you in examination. Okay, so be ready for it. Be ready for it. So it's nothing but one compatibility equation, and that will be first one. So what was that? Dou square on xy plane, dou xy is equal to dou square epsilon y divided by dou x square plus this will be the so only one compatibility equation will be sufficient to satisfy the solution of 3D problems in elastic body. Okay, that's all right.